Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson number 4 on Similarity. Now I've been kind of hinting at similarity all through Unit number 7 if you've been joining us. And today we really formally introduce the idea. And this is something that you definitely saw in 8th grade mathematics. The idea of similarity is very simple. It's the idea that you've got two geometric objects that have the same shape, but possibly and almost always different sizes. And today what we'll do is we'll be getting into the technical definition of what makes figures similar, how to justify that they're similar, and things like that. So let's jump right into the lesson. All right, similar figures. Two figures are similar, and we're going to use that symbol. If all pairs of corresponding sides are proportional, we'll talk about what that means, and the corresponding angles are of equal measure. Okay, so let's just take a look at a couple triangles, right? So here we've got a triangle that has sides of 3, 4, and 5, and another triangle with sides of 9, 12, and 15. So first, let's talk about what it means for the corresponding sides to be proportional. And what that means is if I take the 12, which is the side that corresponds to the 4, right, and I divide them, I get 3. If I take the 9, which corresponds to the 3, and I divide them, I get 3. If I take the 15 and the 5, and I divide them, I get 3. So in other words, 12 divided by 4 is equal to the 9 divided by 3, that almost looks like a 9, which is equal to the 15 divided by 5. This is what it means for the sides to be proportional to one another. And that probably looks similar to that whole scale factor issue that we've been talking about. And then the other piece is that the angles have to be equal, all right? 37 degrees, 37 degrees, 53 degrees, 53 degrees, 90 degrees, 90 degrees, all right? So two figures will be similar if all the angles inside the figure are the same as the angles inside of the other figure, and the side lengths are proportional to one another, which means when you divide two side lengths that are in the same place on the figure, corresponding parts, okay, now aren't congruent, but are proportional, right? So 9 divided by 3 equals 15 divided by 5 equals 12 divided by 4. All right? That's just the definition of similar figures. Okay? So, let's keep going. Exercise number 1. In the diagram below, we know that triangle ABC is similar to triangle DEF. Use tracing paper to verify all corresponding angle pairs between the two triangles are the same measure. All right? So what I'd like you to do is kind of what I've done. Take your tracing paper out and trace over triangle ABC. ABC. Take a moment to do that. All right. This is similar to something that we did in another lesson. And now what we're going to do is we're going to verify all the angles of this triangle are equal to all the angles of this triangle. And we'll do that very simply by just kind of doing this. Oh yeah, look at that. Lies on top there. Right? Same deal. That angle's the same. And let's see if I can do this without turning my head at all. And that angle is the same. Right? So it's easy to now verify that all three angles of the smaller triangle are congruent to all three angles of the larger triangle. Now, letter B says, solve for the missing side lengths of both triangles, show your work, or explain your reasoning. Okay, this gets into the idea that the side lengths of similar triangles or similar figures in general are proportional to one another. Okay, so this is sort of how we would do it. We find two side lengths that are in the same spot on a given triangle. So the 14 and the 7 are corresponding sides of these two similar triangles. And what we can now say is if I take that 14 and I divide it by 7, that's going to be the same as if I take this side, EF or FE, and I divide it by this side that corresponds to it, which is 8. And because FE is the only thing I don't know here, I can easily solve for it. Now, you probably already realize something very simple, which is that, right, 14 divided by 7 is 2. So what this means is, given that this is 2, I'll just kind of swing it around there. All right, I can just multiply both sides by 8, and FE must be 16. right? Now, likewise, right, if I want to know the length of AB, what I can do is I can do something like, I could stick with the 14 and the 7. I could say that 14 divided by 7 is equal to 20 divided by AB, right? And then I could solve this particular proportion, again, simplifying that 14 divided by 7 into 2, or I could just do cross multiplication as well, right? In fact, if I didn't have such a nice simplification and I just wanted to cross multiply, right, I could say 14 times AB is equal to 7 times 20, which is 140. And then I could divide both sides by 14, and AB was equal to 10. All right. Now, if you know anything about similarity, right, it's all about all the sides on this triangle being some multiple of the sides of this triangle. So right away, you may have been able to say, well, that one's 7 and that one's 14. Therefore, all the side lengths on this triangle will be twice the length of all of them on this triangle. And then it's very easy. Then we can just say, well, if that's 8, then that has to be 16. And if that's 20, that has to be 10. Most of the time, the dilation constant, okay, because that's what it really is, the dilation constant won't be this nice number like 2 or 3 or something obvious. It might be more challenging, in which case the kind of cross multiplying is a no-fail way to figure it out. All right? But again, it's all about being able to set up these proportions, cross multiplying, and solving for a single missing side. Speaking about dilations, letter C says, give a dilation of ABC that would guarantee that its image, A prime, B prime, C prime, is congruent to DEF. How do you know it's congruent? All right. So let's talk about dilating ABC. Okay. Well, let's dilate triangle ABC by a factor of k equals 2, and really any center. Any center. Really doesn't matter. All I need is the image of this triangle to be congruent to this one. I don't need it to lie on top of this one. I just need it to be congruent to it. Well, once we do that, right, what will happen is that we will then have A prime, C prime, B prime, right? We would have this to be 14, this would be 16, right? And what we would know, you know, even after given all the other work that we have, what we would now know is we would know that all the angles of these two triangles were the same, right? And all the side lengths would also be the same, right? They would all be the same length. In fact, we would know, since we knew back in the first part of the problem that this is 10, that this would now be 20, right? We also learned in the last problem that this was 16, right? Yeah. And so we could justify it in many different ways. We could now say that by the side-side-side theorem, these two triangles would now be congruent. We could say by the side-angle-side theorem, by the angle-side-angle theorem. We could do a lot of things. And in fact, if we didn't even have, let's say, these two other things listed, if we just had these two, it would be enough by the angle-side-angle theorem. It would be enough by the angle-side-angle theorem to know that the two triangles were congruent. Because remember, dilations don't change angle measurements. So this angle would be the same as this angle. This angle would be the same as this angle, right? And therefore, we could say, I got an angle equal to an angle, a side equal to a side, and an angle equal to an angle. So the two triangles would have to be congruent. Now, this is important because it's going to lead us to the technical definition of similarity. And let's take a look at that. All right. It's what's called, or it involves what are known as similarity transformations. And let me read through this and let's talk about it. Two geometric figures are similar if there exists a similarity transformation that will map one figure onto the other. That should sound familiar. One figure onto the other. This transformation is either a dilation alone or a dilation in combination with one or more rigid motions. I want to just kind of backtrack on this a little bit. This is very, very similar to the definition of congruence. All right, back from Unit 2, we saw that two figures were congruent if there was a sequence of one or more rigid motions that would map one figure on top of the other. Then we kind of got out of that when we looked at, side, 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 angle, things like that. But ultimately speaking, from a transformation perspective, if we could use either a translation, a rotation, a reflection, or a combination of those three to map one figure on top of the other, then they were congruent. Now what we've got is if a combination of rigid motions with a dilation maps one figure on top of the other, then they're similar. All right? So similarity is all about dilations. It's all about dilations. Okay? And again, it's kind of a neat idea. These two triangles are similar. All right? So if somehow I was able to take this triangle and let's say translate it so that A prime, came over here and landed on D, and then I was able to stretch the triangle out. Now, one thing that's a little bit unfortunate about this program is that the dilation center is always at the corner of this rectangular box. So the center of dilation is always up here, which is a little bit tricky. But notice, with that translation, a dilation, and then I guess another translation back, right, I was able to map this particular triangle on top of this one. But make no doubt about it, when I have this geometric figure and I'm doing this kind of thing with it, what I'm doing is I'm dilating it. With this as its center, whoops, I guess I didn't really want to do that. All right, and therefore it allows me to kind of see that these two things are similar figures. And that's what we're going to be working with actually for the rest of this lesson, is just how can we identify and describe these similarity transformations that will map one figure onto another one and therefore prove that the two figures are similar. So let's take a look at that. Now these can be fairly challenging, and we're going to start off with one that's kind of tough. Let's take a look at this. Exercise 2. Given that triangle ABC and DEF below are similar, with congruent angles marked, give a similarity transformation that would map triangle ABC onto triangle DEF using tracing paper to help. Be as specific as possible. Okay, be as specific as possible. All right, and again, this can be rather challenging, especially if you don't have tracing paper to work with. So pause for a moment, take out some tracing paper, trace out triangle ABC like I've done. I would even suggest like writing on point A, point B, point C, and then we'll take it from there. All right, let's take a look and let's talk about how we're going to do this. All right, so step 1. All right, I'm going to translate I'm going to translate the whole triangle, but I'm going to translate it in a way that's going to take one of the 3 vertices and map it so it lies on top of the corresponding one. Now for me, the one that's most obvious is to transform it so that, or translate it so that B prime lands on C. So translate triangle ABC so that B maps to E. Now technically that means that we've got B prime sitting here. All right, so I've taken this whole thing and I've kind of moved it over there. Now what I'd like to do, notice how A and D are the same, right, with that one kind of angle arc mark there. What I'd like to do is I'd like to rotate this thing up, okay? So I'm going to rotate, and at this point it's really rotate triangle A prime, B prime, C prime about E so that, and I know it didn't rotate it about E, but so that it would now be A double prime, B double prime lies on ED. All right. Now notice how similar this figure is now to those figures that we've been looking at all along with dilations, right? And we're now at the point where we've got a dilation, right? Or where we should use a dilation. Now what I'd like is to stretch this red triangle out, right? So now I'm going to dilate. I'm going to dilate triangle A prime, B prime, C prime with a center at E, right? I don't want that to move. And now I have to give a dilation factor. Now remember, what I really want is I sort of want this length to stretch up, so that it's that length, right? So what is that a little bit? With a center at E and a dilation constant of K equals, remember, new divided by old, and that would be the new length would be ED divided by the old length, which is actually AB. And you could say A double prime, D double prime, that would be okay as well. Everything up to now has been a rigid motion, so it hasn't changed lengths. Now you might say, well, why did I take length AD and divide it by length AB, or sorry, ED, and divide it by length AB as opposed to something else? Because I could have also gone with, let's say, EF divided by BC. And the answer is, it could be any of them. All right, as long as you take the newer length and you divide it by an older length, that would be okay. So ED divided by AB would be fine. Let's see what else would be okay. What else would be okay would be EF divided by BC, or you could even say DF divided by AC. Okay, any of those, right, will be the same constant because that's the idea of similarity. All right, it would stretch out, and it would stretch out, right? Eventually what would happen, again, this is going to change my center of dilation, but is that those two would sit right on top of each other. Okay, so a series of rigid motions, okay, followed up by a dilation. And the idea is always when you've got that series of rigid motions is you eventually want a picture that kind of looks like this, right? Where essentially the two similar triangles are oriented in the same way, and then you use that vertex that's been matched up as the center of your dilation, then take as your dilation constant a new length that you want divided by an old length that you have. They've got to be the corresponding side lengths, and you have that similarity transformation. It's going to be kind of tricky, all right? There's no doubt about it. A little bit harder than those rigid motion transformations to prove congruence. Let me step out of the way. Go ahead and write down anything you need to, and then we'll move on and we'll do another one of these. All right, let's do it. Okay, another one, right away. Exercise number 3. In the following diagram, it's known that BCN and ACM and ABC is similar to MNC. Give a similarity transformation that would map ABC onto MCN. Use tracing paper to help visualize the rigid motions. Okay, same idea. I want to somehow map ABC onto MNC using a similarity transformation. Now, this is kind of critical, right? BCN and ACM, these seem like they're kind of like toss-ins. All that's really doing is telling you that these are collinear and these 3 points are collinear. All right, so let's try to get these things to match up. Now before we began with a translation. Here, I can go a little bit easier than that actually. I can simply rotate triangle ABC about C by 180 degrees. I can just do this. All right. And if I had everything perfect on this picture, it would just kind of line up like that. And notice we already are kind of in that situation that took us 2 steps in the last problem to get to. This one's actually a little bit easier, right? I'm already at a point where I'm kind of ready to dilate this thing. I'm ready to shrink it down so it lies right on top of that. So the second piece is the dilation. Now I'm going to dilate triangle A prime, B prime, C prime, okay? But what I'd like you to do now is tell me, or try to figure out, what is the center of dilation and what should I use as the scaling factor? All right, let's talk about it. Well, the center is no question. With a center at C and a scaling factor of, and here's where you have lots of choices again, all right? Lots and lots and lots of choices. We just have to go old length divided by new length. So for instance, I could take the length of BC, which is really this length right here, the length of BC, all right? That's, remember, we always want to do new divided by old, maybe even write that down, new divided by old. And the new length that I'd want BC to be would be NC, or CN, and then we would divide it by the old length, BC, all right? So if I took the new length that I want it to be, NC or CN, and I divide it by the old length, BC or CB, right, that will then compress it down so that this length here becomes this length here. And all the other ones will kind of follow along because all these corresponding sides are proportional to one another, all right? But those aren't our only choices, okay? Another thing that you could do is you could say, well, I could take length MN, all right, that's my new length, and I could divide it by my old length, length AB. Now you only need one of these. I'm just showing all the different choices. And finally, we could also do the length of CM or MC, and we could divide it by the length of AC. That scaling factor, which is very important, you'll certainly be tested on it repeatedly. That scaling factor will always be the newer length, the triangle you're trying to transform into, divided by an older length, the triangle that you started with. Since we're starting with this larger triangle and going to this smaller one, we always want to take a length off of this smaller one and divide it by a length on that larger one. When we do that, eventually what would happen is we would get two triangles, maybe get two triangles that are congruent. Something like that. All right? Similarity transformations, rigid body motions combined with dilations. Now, side note, you could do the dilation first. All right, I always tend to do the dilation last. I make sure I get it so that the two triangles are oriented in the same way and they share a vertex, they share one of the 3 points, and then I use that point, that shared point, as the center of dilation and then stretch it out using a constant that's a new length divided by an old length. All right, let's keep moving along. Ah, the coordinate plane. Love being back into the coordinate plane. There we can count, we can measure, we can see all sorts of stuff. So let's take a look at this problem. Given triangle ABC is similar to triangle DEF on the grid shown, what is the scaling factor needed to dilate ABC so that it is congruent to DEF? Show how you arrived at your answer. So in this one, we can actually come up with a hard number. It's going to be, okay, my scaling factor is 3, or it's 1/3, or something like that. See if you can figure out what the scaling factor is. Okay, remember, to dilate ABC, so this is the old, to get DEF, and that's the new. Go ahead, think about that for a minute. All right, let's go through it. Well, all you really have to do is come up with two sides that correspond to one another and divide their lengths, taking the new length and dividing it by the older length. 2 of the 3 lengths are very, very convenient. One of them is not, and that's that hypotenuse. For me, I would simply take the length of DE, which looks to be 6 units long, and divide it by the length of AB, which is 4 units long. And when I do that, I would get a dilation constant of 1.5. Or 3/2, you could leave it as in fraction form. You would get exactly the same thing if you took the length of EF, which is 12, and you divided it by the length of BC, which is 8. And that is also 3/2, or 1.5. Again, new divided by old. If we were going the other way around, by the way, if they had said, well, what dilation constant would you have to use to make DEF congruent to ABC, then both of these fractions would be reversed and we'd get a dilation factor of 2/3 or 0.666 repeated, 0.67 if you rounded it to a reasonable amount. Remember that direction matters because are we taking a smaller object and making it larger or vice versa? Let's take a look at letter B. Specify a similarity transformation that would map ABC onto DEF. All right, well, let me get rid of all this mess so that we can kind of look at this a little bit easier. So now I want that step 1, step 2, step 3 thing. Why don't you go ahead and take a shot at this, okay? There's many different correct answers. We'll take a look at one of them. All right, let's go through it. I'm going to even try to trace out ABC to see if I've got a working model that I can trace with. Hopefully that'll work. Lovely. All right. So let's do it. I want to do exactly what I did before. I want to get 2 vertices matching up that I know have the same angle. And probably the easiest thing to do is get B to match up with E. So first thing I'm going to do is I'm going to translate triangle ABC so that B maps to E. So this thing is going to come up kind of like that, right? All right, that's not bad. Now what I'd like to do though is I'd like to have it in the same orientation. So I want to reflect that. So the second thing I'm going to do is I'm going to reflect triangle A prime, B prime, C prime across what? Well, you could describe it in many different ways. I want to reflect it across this vertical line. So you could give that equation. You could say, I'm going to cross the line x equals 3. That's that vertical line. Or you could just say across EF, right? You don't even have to use the equation, even though we're in the coordinate grid. You could just say, I'm going to reflect it across EF. Let's do that. Hopefully it will allow me to. Let's flip this thing left, right. All right. And that would end up, whoops, making it look kind of like that. I won't waste your time by trying to get it exactly. But now again, look, we've got the 2 triangles in exactly the same orientation. So now all we need is that final dilation piece. Let me bring it up just a little bit. And now let's dilate triangle A double prime, B double prime, C double prime with a center at E. And we've already figured out the constant and a scale factor. There's my magic red. Scale factor of K equals 1.5. All right. I like the coordinate grid because oftentimes we can give that scale factor in a precise numerical form. We don't just have to say, oh, it's DE divided by BC or something like that. We can literally say, okay, I did the division and I got 1.5. Let me step out of the way for a second so you can take a look at this and then we'll move on to do more. All right, let's take a look at the last problem. Here we go. Exercise number 5. In the diagram below, A, B, and C are collinear as well as A, D, and E. It's also known that BD is parallel to CE. All right, I'm going to mark that on my diagram right away. BD is parallel to CE. Give a dilation that would map ABD onto ACE. All right, this is actually pretty simple. Why don't you go ahead and do it? All right, the reason that this is fairly simple is that we don't have to give any rigid body motions to get the triangles in the same orientation. They're already sitting there. And hopefully, to get ABD, the smaller triangle, to map onto ACE, the larger triangle, we would just simply do this. Use a center at A and a scale factor and this is where you got some choice, a scale factor of k equals new divided by old. So I could say AC divided by AB, or AE divided by AD, or CE, divided by BD. Okay? Any of those ratios where I've taken the newer length, in this case the length of the larger triangle, and divided it by a length of the smaller triangle, will get the job done. We'll never know exactly what that is numerically because we don't have any dimensions on this picture. Now the last part of this triangle is the last part of this problem is pretty challenging. Let's take a look at it. It says circle the proportion that is incorrect based on the fact that triangle ABD is similar to triangle ACE. All right. Now, one thing I'm going to do is I'm going to draw these two triangles separately. Not a bad idea ever, and then we'll kind of move the thing up a bit. So the smaller triangle is ABD, all but done. The larger triangle is ACE, and I can't even make a silly pun out of that one. Certainly not an ace. Okay, so let's take a look, right? Which of these proportions is incorrect? Well, let's take a look at it. It says AC divided by AB. So what would that be? I could kind of think of that as, maybe move this down here, and my letters as well. Okay, so AC divided by AB. That's large divided by small equals CE divided by BD. That's large divided by small. That's fine. Okay, that's, this larger side divided by the corresponding smaller side, this larger side divided by this corresponding smaller side. So that one's fine. Now the angles. The measure of angle A, this thing, divided by the measure of angle ABD, so this one divided by this one, or better yet this one, they're the same angle, is equal to the measure of angle A divided by the measure of angle ACE. Well, keep in mind that all the angles in the two triangles are the same, all the corresponding angle pairs. So A divided by ABD is equal to A divided by ACE. ACE is the same because it's sort of single arc divided by double arc equals single arc divided by double arc. Right here, it's not that the angles are proportional to another, the angles are literally equal. So you can really track that with the arcs. If I've kind of got this measured out nicely, single arc divided by double arc is equal to single arc divided by double arc. So that works fine too. Let's take a look at number 3. Number 3 says AD divided by AE, right? AD divided by AE, that's going to be small, divided by AE, large, is equal to AC, large, divided by AB, small. No. The order's got to stay the same. So if I'm taking a length from the small triangle, dividing it by a corresponding length of the large triangle, then I'd have to have a length from the small triangle divided by a length from the large triangle. So this is actually the correct choice because it's an incorrect ratio. We could look back at this as well, right? If we looked at this one, AEC, that's sort of a double arc angle divided by ACE. Whoops. Wait, AEC, no, that's triple. Triple arc divided by ACE, double. ADB, triple, divided by ABD, double. All right, so that one's fine as well. We didn't really need to do that once we knew this one was wrong. All right. And again, that can be a little bit tricky because we don't have numbers, we don't have ratios. Some people may still be a little bit uncomfortable with ratios and division and things like that. But remember, these proportions always have to stay the same. Small divided by large has to be small divided by large, right? Because that's that dilation constant. Not with the angles, but with the side lengths. And that dilation constant multiplies all the sides and changes them. All right, so let's wrap it up. Similarity, the idea that two figures have the same shape but different sizes. What does it mean to have the same shape? It means that all the angles are the same and all corresponding side lengths are in proportion to one another. So if I've got two triangles, all the angles are the same, but if one side in the larger triangle is twice the length of another side in the smaller triangle, then all the sides have to be twice the length. Okay? So we then introduce the idea of a similarity transformation, which is very similar to a congruence. In other words, I've got to use transformations to map one of these figures, typically a triangle, on top of the other. The difference now is not only do we have the three classic rigid motions, translations, rotations, and reflections, but we then throw in a dilation in order to stretch or compress one of these figures so that it lies directly on top of the other. All right, we'll work a little bit more with this in the next lesson. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.